teleportation is no longer a science fiction world. Thanks to quantum mechanics, people can teleport information from one place to another.
In late 2022, researchers announced a breakthrough experiment in quantum teleportation, sparking widespread attention and even some sensational claims online. A few discussions went as far as suggesting that MIT's mysterious quantum afterimage appeared following a teleportation run.
A theory that describes the properties of quantum objects, such as atoms and, well, photons.
But what exactly does this mean? And what are these so-called quantum teleportation experiments really about? In this video, we'll break it down and answer all your questions. So, let's get started. MIT's wormhole-inspired teleportation simulation. In December 2022, an international team of researchers from the Massachusetts Institute of Technology, the California Institute of Technology, Harvard University, and Google Quantum AI published a landmark paper in Nature that instantly drew global attention. The study was heralded as one of the first practical demonstrations of a phenomenon long confined to the realm of theory: teleportation through a simulated wormhole. This was the first successful transfer of quantum information across an engineered system that behaved mathematically like a traversable wormhole. This breakthrough marked a crucial intersection of quantum information science and theoretical physics, bringing concepts from Einstein's theory of general relativity and string theory into contact with laboratory results for the first time. Caltech and Harvard contributed their deep theoretical expertise in high-energy physics and the mathematical framework of holography, while MIT provided quantum information theorists and computational modeling expertise. Google Quantum AI brought to the table its powerful Sycamore quantum processor, which had already been used in 2019 to demonstrate a form of quantum supremacy by performing a calculation that would have taken classical supercomputers thousands of years. The blending of these distinct strengths created the perfect environment for testing ideas that had previously only been explored on paper. So, how big of a deal is it, really? Well, it's huge. The Nature paper was formally titled Traversable Wormhole Dynamics on a Quantum Processor, and it represented the culmination of years of effort to bring holographic duality, a central concept in modern theoretical physics, into contact with real quantum systems. The principle underlying this work is the anti-de Sitter conformal field theory correspondence, better known as ADS-CFT, first proposed by physicist Juan Maldacena in 1997 at Princeton's Institute for Advanced Study. Maldacina's insight was that certain strongly interacting quantum systems can be equivalently described as gravitational systems in a curved, higher-dimensional space. In other words, phenomena that appear as black holes or wormholes in one description can be reformulated as interactions between particles in a lower-dimensional quantum field theory. This duality has been one of the most influential ideas in physics over the last quarter-century, and the MIT, Caltech, Harvard, Google collaboration sought to give it experimental form. The experimental setup was intricate. Instead of attempting to create an actual wormhole, a structure that would require exotic matter with negative energy density and is not known to exist in the physical universe, the team built a quantum circuit that could mimic the mathematics of wormhole traversal. The system was constructed on Google's Sycamore quantum processor, which is a superconducting device with dozens of qubits cooled to near absolute zero. Qubits, the quantum equivalent of classical bits, can exist in superpositions of states and can be entangled with one another, meaning their properties are correlated across distance in ways that defy classical expectations. For the experiment, the team designed two entangled sets of qubits that served as the two ends of a simulated wormhole. Once the entangled systems were established, the researchers followed a carefully designed protocol. They inserted a qubit of information into one side of the entangled system. To simulate the conditions of a traversable wormhole, they applied a sequence of engineered interactions that the team referred to as a shockwave. This shockwave was not a physical disturbance, but a controlled manipulation of the system's Hamiltonian, the operator that defines the energy and dynamics of a quantum system. The result of this manipulation was that the quantum information injected into one side of the system emerged on the other side, in a manner consistent with what one would expect if it had passed through a wormhole. One of the most important aspects of this result is what did not happen. The transmission of quantum information did not occur faster than light, nor did it involve the transport of mass or energy. The signal moved within the strict limits of causality set by both quantum mechanics and special relativity. In fact, the classical communication channel required to complete the teleportation protocol still enforced that nothing could happen in a way that violated Einstein's cosmic speed limit. This ensured that the experiment, while exotic in its design, remained firmly consistent with the laws of physics as they are currently understood. The successful demonstration had enormous implications. First, it showed that wormhole-like behavior could be recreated in a laboratory setting using existing quantum technology. This does not mean that scientists are on the brink of creating real wormholes that people or spacecraft can travel through, but it does mean that some of the most challenging and abstract ideas in theoretical physics can now be probed through direct experiments. Second, the result provided an important proof of concept for the link between quantum entanglement and the geometry of spacetime. Physicists such as Leonard Susskind at Stanford and Juan Maldacena have argued for years that entanglement is the glue that holds spacetime together, with wormholes representing a geometric manifestation of entangled states. The MIT-led team's experiment gave the first tangible evidence that such an interpretation can be mapped onto working quantum devices. The use of Sycamore's quantum processor was crucial in making this possible. Unlike classical computers, which would require astronomical resources to simulate entangled systems of this complexity, Sycamore could directly implement the quantum circuits needed to test the wormhole protocol. The processor used in this experiment did not employ its full complement of qubits, but rather a tailored subset configured specifically for the test. By fine-tuning the interactions, the team was able to compress the dynamics of a complex many-body system into a manageable number of qubits while still preserving the essential mathematical structure. Such is the direction of modern physics: results, reactions, and context. The key results of the experiment were not only that information was successfully transmitted in a wormhole-like manner, but that the transmission preserved quantum coherence, the hallmark of true quantum information transfer. The qubit that emerged on the opposite side of the entangled system was demonstrably the same quantum state that had been input, reconstructed without being copied in violation of the no-cloning theorem. This is the essence of quantum teleportation, which has been demonstrated many times before between photons, trapped ions, and other systems, but never before in a configuration designed to mimic the dynamics of general relativity. The novelty here was not the teleportation itself, but the context. Teleportation that looked mathematically indistinguishable from traveling through a wormhole. The publication in Nature sparked a lively discussion across the scientific community. Some physicists hailed the experiment as a milestone, suggesting it represented the first step toward uniting quantum mechanics and gravity in a testable framework. Others were more cautious, noting that while the analogy to wormholes was mathematically valid, the system itself was still far removed from the vast complexity of actual spacetime. For example, the experiment operated with only a handful of qubits and under highly engineered conditions, whereas a real traversable wormhole, if it exists, would involve astronomical scales of energy and matter. Nonetheless, even the skeptics agreed that the study opened a new window into testing ideas once thought to be permanently beyond experimental reach. The MIT-led collaboration points toward a future where quantum processors are not only tools for computing, but also laboratories for simulating fundamental aspects of the universe. Quantum field theories that describe particle physics are notoriously difficult to simulate on classical machines, especially in regimes of strong coupling. Quantum computers, however, can in principle model these systems directly, offering insights into phenomena such as quark confinement, phase transitions in the early universe, and perhaps even the quantum structure of black holes. The wormhole simulation was proof that these ambitions are not purely speculative, but can be realized in practice. This research did not emerge in a vacuum. For decades, physicists have speculated about the role of entanglement in shaping the fabric of reality. John Bell's pioneering work in the 1960s on quantum correlations, and Alain Aspect's Nobel Prize-winning experiments in the 1980s, verifying the non-local nature of entanglement, laid the foundation. Later, the development of quantum teleportation protocols in the 1990s by Charles Bennett and colleagues at IBM showed that quantum information could indeed be transmitted between distant parties using entanglement and classical communication. By the early 2000s, experiments had demonstrated teleportation over distances of several kilometers using entangled photons. Each of these milestones paved the way for the more ambitious step taken by MIT and its collaborators in 2022. Looking forward, the implications of the wormhole-inspired teleportation simulation extend beyond theoretical physics. One of the most practical applications lies in the development of a quantum internet, a network that would allow quantum information to be transmitted securely across global distances. Teleportation protocols are a key ingredient in such a system, ensuring that information can be sent without interception or duplication. The lessons learned from the wormhole simulation, particularly the preservation of coherence and the control of engineered interactions, could feed directly into the architecture of next-generation communication networks. But that's a lot of information to digest. Why don't we move back to the basics? Fundamentals of quantum teleportation. Quantum teleportation is one of the most counterintuitive, yet rigorously demonstrated phenomena in modern physics, sitting at the intersection of quantum mechanics, information theory, and communication science. Since its theoretical proposal in 1993 by Charles Bennett and colleagues at IBM, teleportation has grown from a mathematical protocol into a practical technique implemented in laboratories and even across real-world fiber optic networks. The concept does not involve the physical transport of matter as depicted in science fiction, but rather the transfer of the precise quantum state of a particle from one location to another. This process hinges on the peculiar properties of quantum entanglement and requires a carefully orchestrated interplay of quantum and classical information. So, here's how the standard protocol for quantum teleportation works. Think of Alice and Bob as two friends who each have a pair of magical dice. By the way, Alice and Bob are the terms used to refer to the sender and recipient in such protocols. These dice are special because they're connected in a mysterious way. Whenever Alice rolls hers, Bob's dice instantly show a matching result, even if he's sitting on the other side of the planet. That strange connection is what scientists call entanglement. Now, let's say Alice has a secret recipe written on a piece of paper. She wants Bob to have it, but there's a catch. She can't just photocopy it and send it. The rules of the universe don't allow making a perfect copy of this recipe. Instead, she has to find a clever trick. Here's how it works. Alice takes her recipe and locks it inside her magical dice. When she does this, the recipe at her end disappears, but her action scrambles Bob's dice in a way that now secretly contains her recipe. But it looks like gibberish at first. To finish the job, Alice sends Bob a quick text message with two simple instructions, such as just turn the page twice or flip it upside down. These are the two classical bits of information. Bob follows the instructions, and suddenly the recipe appears on his dice exactly as Alice had it before. The magic here is that the recipe itself has moved from Alice to Bob without anything physical traveling between them. Alice no longer has it because it exists only with Bob now. This is quantum teleportation in a nutshell. Seems like magic, doesn't it? Well, it's very real, but it does come with its own set of limitations. For starters, quantum teleportation cannot be used for faster-than-light communication. The classical channel, which requires the exchange of two bits of information, sets a hard limit. The reconstructed state at Bob's side cannot be known until Alice's message arrives by conventional means, bounded by the speed of light. Even though entanglement correlations appear instantaneously across distance, the usable information is locked behind this causal bottleneck. This prevents any violation of relativity, preserving the consistency of physical law. The teleportation also does not move mass or energy. Unlike the beaming of objects in popular culture, nothing physical is transferred from Alice to Bob. Only the abstract description of the quantum state is sent, encoded into the correlations of entanglement and the classical correction. This means that quantum teleportation cannot be used to transport people, objects, or energy across space. Instead, it is a tool for transferring the state of a system, which, while intangible, is the most crucial ingredient for emerging quantum technologies. The third constraint is the no-cloning theorem, which underpins why teleportation is remarkable but not paradoxical. In classical information, it is trivial to make copies. A string of bits can be duplicated endlessly without loss. In quantum mechanics, however, unknown states cannot be cloned perfectly. This principle, mathematically proven in the early 1980s, ensures that Alice's state cannot remain with her while also being recreated for Bob. Teleportation is therefore not duplication, but transfer. Despite these limitations, the revolutionary potential of quantum teleportation lies in what it enables. Since the first experimental demonstration in 1997, performed by Anton Zeilinger's group at the University of Innsbruck, with entangled photons over a distance of about 1 meter, the technique has advanced dramatically. In 2015, researchers at the University of Science and Technology of China achieved teleportation of qubits across a distance of 100 kilometers using free space optical links. 2 years later, the same team reported quantum teleportation from the ground to the Mikius satellite, orbiting at an altitude of 500 kilometers, a feat that set a world record and showcased the viability of global-scale quantum communication. These experiments are laying the foundation for what is now called the quantum internet. The vision of a quantum internet is a global network where quantum states can be transmitted securely and instantaneously across vast distances. Because of the laws of quantum mechanics, such a network would offer unbreakable security against eavesdropping. Any attempt to intercept a quantum transmission would irreversibly disturb the system, alerting the parties involved. Teleportation, which allows the faithful transfer of quantum states without exposing them to direct measurement during transit, is a cornerstone of this vision. Linking quantum processors through teleportation could also enable distributed quantum computing, where complex calculations are divided among nodes and then recombined, dramatically increasing computational power. The implications of teleportation extend even further into the realm of physics itself. By treating quantum information as something that can be moved and manipulated, researchers are gaining insights into the nature of entanglement and its relationship to the structure of space-time. Prominent theorists like Leonard Susskind at Stanford University and Juan Maldacena at the Institute for Advanced Study have argued that entanglement is directly connected to the geometry of the universe, with wormholes representing physical manifestations of entangled states. While teleportation as practiced today is firmly within the bounds of quantum mechanics, its role in linking information with geometry could ultimately help physicists address the most profound question of all: how to unify quantum mechanics with general relativity. For all these reasons, teleportation remains a field of intense study. Laboratories around the world continue to push the boundaries of distance, fidelity, and efficiency. The Delft University of Technology in the Netherlands, for instance, has performed teleportation with solid-state qubits embedded in diamond, while groups in Japan, Austria, and Canada are working on integrating teleportation into existing fiber optic infrastructure. If it sounds futuristic, that's because it is. But this rapid advancement has also led to misinterpretations. Let's address them. Clarifications against misinterpretations. When news broke in 2022 that MIT and its collaborators had simulated a wormhole on a quantum computer, some reports drifted towards science fiction language, suggesting after-images or ghostly duplicates appeared during teleportation. In reality, nothing of the kind happened. If it had, it would have shattered one of the cornerstones of physics, the no-cloning theorem, established in 1982 by William Wouters and Wojciech Zurek, which proves it is impossible to create perfect copies of an unknown quantum state. This principle is what keeps the entire framework of quantum mechanics internally consistent. Also, the team, working in collaboration with Caltech, Harvard, and Google Quantum AI, did not teleport an object or a person. Instead, they teleported quantum information, meaning the state of a qubit, across two small entangled quantum systems running on Google's Sycamore processor. To make this transfer work, they designed the protocol so that the information sent into one side could be recovered on the other side, in a process mathematically equivalent to what physicists describe as sending information through a traversable wormhole. No matter what was moved, no duplicates emerged. Instead, the original state was destroyed at the sender's end, as the information was reconstructed at the receiver's end. That is what distinguishes quantum teleportation from the popular imagination of teleportation in science fiction. When most people hear teleportation, they think of bodies vanishing in one location and reappearing whole somewhere else, as if matter itself had been disassembled and reconstructed at a distance. That image is rooted in cultural touchstones like Star Trek's transporters or Marvel's portals. But real quantum teleportation does not move atoms, molecules, or energy across space. It moves only the information that describes a quantum state, and it does so under strict rules set by entanglement and classical communication. In fact, because the original quantum state is destroyed during the process, teleportation ensures that no copy is left behind, no after-image, no duplicate, no ghostly residue. Beyond the myth-busting, the work highlighted how far quantum computing has advanced. Google's Sycamore had already made headlines for quantum supremacy in 2019, and by 2022, it was probing the physics of space-time itself. Though the experiment used only a handful of qubits, it showed how future processors with hundreds or thousands could simulate even richer models of gravity and cosmology. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.